Hi everyone, I'm David Aliou, I'm product manager at Cailabs, and today I'm going to talk about laser communication. I guess you all heard about 5G and satellite constellation telecommunication and Earth observation, very high resolution imaging. And I'm pretty sure that some of you are developing some products or components for this application, and I'm pretty sure that you know much more about it than I do. At Cailabs, what we do is we do some optical beam shaping, and there are many applications for optical beam shaping. The one I'm going to talk today is how to improve laser communication thanks to beam shaping. In all of the applications that I mentioned previously, and especially in Earth observation and telecommunication, you need very high throughput, very high data rate. And a lot of new applications are creating and will create new needs for very high throughput and very high networks. We can quote, it's not working. We can think about drone and plane and satellite networks. And for all of this, you will need new usage. You will have new usage, and you will need very high throughput. And sorry.
Point it that way. Pointer comme ça. Devant toi.
Oui. No. What do you mean? Ah, okay. Whoa, what the f... Okay. It's really weird, sorry. I'm really sorry. And okay.
That came out.
Very naturally. Currently, the technology for telecommunication is radio frequency. And radio frequency is very good when you want to have typically 100 to 1 gigabyte per second telecommunication link. But when you want to go beyond that, typically to 1 to 100 gigabyte per second, it becomes very complicated with radio frequency. Moreover, radio frequency is something where you have frequency allocation, when you have licensing. And especially with the coming of 5G, it becomes really saturated, and it will become even more. Finally, one of the last problems with radio frequency is that it's very relatively easy to detect and to intercept. And all of these drawbacks of radio frequency, I would say, are advantages of laser communication. It is a technology that is very fast, that is very relatively hard to intercept, and you don't need licensing. But of course, you will say, if it's that easy and that powerful, why isn't it already widespread everywhere and that everybody is using laser communication? The answer is, of course, there are a lot of drawbacks also of laser communication, and the main one is the atmospheric turbulence. When the beam propagates, it is modified, its wavefront profile is modified by the atmospheric turbulence, and which degrades the link performances. There are, of course, some technology to mitigate that, like adaptive optics, for example, but these technologies are very bulky, they are very expensive, relatively hard to integrate, and typically, if you want to put that inside a plane, it's very complicated. This is exactly why we are developing new components. At Cailabs, what we do, it's optical beam shaping. We have a unique technology that enables us to manipulate very precisely the shape of the light, and especially to manipulate multiple beams at the same time. Thanks to a succession of reflection on a faceplate and free space propagation, we're able to generate more or less any shape that you would be interested in. Typically, we do some square flat top for LiDAR imaging, active imaging. We do some fiber modes for fiber communication, and more complex shapes for material processing. And when you are able to manipulate the shape of the light, you are also able to do some turbulence mitigation. And this is what we are bringing with our components. Typically, if you imagine a link from a satellite to Earth, the beam propagates, is modified, and in the end, you want to couple this beam inside a single-mode fiber, because all the architecture, all the ecosystem for very high-speed communication in optics is based on single-mode fiber. But the profile that is degraded won't couple to a single-mode fiber. This is why, basically, you use adaptive optics. What we do is that, thanks to our multiplexer, demultiplexer, we're able to decompose the light in a superposition of beam profile, of mode, shapes, that we demultiplex to single-mode fibers. This is the first step, but the problem is that you will have several outputs. And basically you don't want several outputs. So we recombine them thanks to a photonic integrated chip to a unique single mode fiber. So you have perturbated beam directly to a single mode fiber. You can imagine it as a black box from free space to single mode fiber. Basically, what we bring at Cailabs is, thanks to beam shaping, being able to enable laser communication by mitigating atmospheric turbulence. We have a standard, relatively standard component that is cost-effective, plug and play, that is airborne compatible, and typically the smallest component that we developed in partnership with Safran for aircraft coupling, so completely different application, is the size of a 2 euro coin and compatible with airborne application. Finally, we performed some first field test with the DLR June last year approximately, that show that we are competitive with state-of-the-art technology, typically adaptive optics, with a much more standard, simpler, and robust component. And what we bring is really to make laser communication simple. Thank you very much for your attention.